Welcome everyone to this impact session on making quantum matter. Just briefly about myself, my name is Alina Mendt. I'm heading an international pitch competition for deep tech startups at the Falling Walls Foundation. Falling Walls is a global hub for leaders from science, business, and politics, and we're promoting scientific breakthroughs. And one of the things that I like most about my job is coming across and learning about pioneering ideas in companies, and because it provides me with such hope and optimism for the future. And this is also one of the reasons why I'm grateful to be part of this event, and why I'm now very excited to introduce to you our speakers for this session, Alexander Glätzle and Dieter Kranzmüller. So Alexander Glätzle is CEO and co-founder of planqc, the company that is developing the first German quantum computer that is based on neutral atoms. Before that, he worked as a senior research fellow at the University of Oxford and at the Center for Quantum Technologies in Singapore, where he researched ultra-cold atoms and quantum annealing. Dieter Kranzmüller is professor of computer science at Ludwig-Maximilians University of Munich. He is chairman of the board of directors of the Leibniz Supercomputing Center of the Bavarian Academy of Sciences and Humanities. He also serves on the board of the German National Gauss Center for Supercomputing. And in this session, they will talk about how close we are to quantum systems that finally matter to industry, or for industry, and showcase how breakthroughs could unlock industrially relevant performance sooner than expected. We will first hear the presentations of 10 to 12 minutes each, and afterwards have a Q&A session. So the stage is yours.
Perfect. Thank you very much for having us here. It's a great pleasure to be here. First question, are there any quantum physicists here in the audience? Perfect. Okay, one and a half? Okay. Well, quantum computing actually has a very long heritage, and it's very deeply rooted to Europe. If today we talk about European sovereignty and deep tech, quantum computing is actually a field which originated very strongly here in Europe, with figures you see here from Planck, Bohr, Schrödinger, and Heisenberg, who really revolutionized that field here. And what they came up is a completely new theory how single atoms interact with single photons, how they collide, how they emit light in different frequencies. And to explain that world, this microscopic world of single atoms, single photons, they have to come up with completely new concepts which are so crazy that still today we struggle to understand them. And one of the most important concepts is superposition. Superposition means that quantum objects like single electrons, photons, can be in two states at the same time. That would be great, right? Being here on that stage and another stage at the same time, or at home with your family. That's something we just simply don't know from our macroscopic world. But an atom can be at two places at the same time, can spin around clockwise or counterclockwise at the same time. Even more crazy, if you take two of them, you can entangle them. So they are highly correlated. If you put one of those particles on the moon, keep one on the Earth, and you would measure one of them, you would instantly also manipulate the other one. That's called entanglement. And the third property is even more crazy. If you don't observe these objects, if you don't watch them, suddenly they behave as waves. If you watch them, then they collapse and suddenly they are a particle again. And if you think, okay, I'm in the wrong room now, this is getting too crazy, then you're in a very good audience, because Richard Feynman, one of my personal idols, already 40 years ago said, I guess nobody understands quantum physics. And what he meant with that is actually that probably our human brains by evolution are just not made to understand these microscopic phenomena. And people like Einstein and many more, they came up with experiment after experiment to actually prove the world that this theory is wrong. The world cannot be that crazy. But every experiment so far proved that quantum mechanics is right. And today it's probably the best proven theory mankind ever created. And it's already in many, many devices. If you use your mobile phones, if you use everywhere where semiconductors are, semiconductors work due to the laws of quantum physics. If you do an MRI scan in a hospital, this is based on the fact that the atomic energy levels are quantized. That's pure quantum mechanics, which allows that these machines work. And even if you use your GPS like me to find the science house today, GPS works because on the satellites there are atomic clocks. The most accurate clocks mankind ever built are based on the laws of quantum mechanics. And the next big revolution is to use quantum physics for calculations, to build super fast computers. And there are some problems, for example, adding numbers, multiplying matrices. This is easy for classical computers. This is very fast. But there are problems out there, for example, in material science, where you want to understand how two molecules combine, how two atoms talk to each other. And they are extremely hard to solve on any classical computer. And there is a big hope, and actually also mathematical proof, that quantum computers can solve such problems, material science, drug discovery, exponentially faster than any supercomputer. Give you a simple example. A single caffeine molecule, and actually I'm missing my coffee today, contains of 24 atoms. And these 24 atoms can be in 10 to the 48 vibrational or rotational states at the same time. 10 to the 48. Probably nobody of us has a feeling what's 10 to the 48, the number with 48 zeros. That's roughly the number of atoms our planet Earth consists of. So if you think that through, storing the information which is in a single caffeine molecule requires a hard disk which uses every single atom of this planet Earth to store this information. That's how ridiculous it is to solve any material science problem where you have quantum physics already included on a classical computer. And it was again Feynman who noted that if you want to simulate nature, if you want to simulate quantum physics, you need a quantum computer. And the basic principle, if you want to understand how a quantum computer works, is look at this labyrinth. If you want to understand or find the ways through the labyrinth, you probably have to try every pass at the same time. A quantum computer would do it like a fluid. It's like putting water into the system which flows through all possible paths, and at the one point where one drop finds the exit, the water this water wave collapses, and you have one river flowing through the labyrinth exactly where's the shortest way. That's the magic of quantum computing. Huge parallelization due to this wave nature. And there are various ways to build quantum computer. The LSZ actually is one of the pioneers hosting very different modalities and trying them out. There are, for example, superconducting qubit. That's what Google or IBM is building. There are ion-trapped systems using charged ions to store information. There are photonic qubits, so using light as the unit of information, and the neutral atoms. That's basically what we are doing as a company. And here's an image. So the heart of our quantum computer, that's basically a vacuum chamber. That's what you see here. This is this glass cube here. And inside this glass cube, there's ultra-high vacuum. And that's where we store single atoms. And each of these single atoms can be in a state 0 or a state 1. So we can manipulate single atoms in such a way that if the outermost valence electron circles clockwise or counterclockwise, that's 0 or 1. And if you do the quantum magic, then they can be in the state 0 and 1 at the same time. We are building here on a huge heritage, founded 2022. We are now around 100 people. Our headquarters is in Munich, very close to the Leibniz Supercomputing Center. We are very proud that we signed contracts with more than 50 million to build quantum computers. We also design algorithms. This is also a very important field. We have to develop use cases which can be potentially run on quantum computers. We are a spin-out of the Max Planck Institute of Quantum Optics, which is one of the, I would say, world-leading institutes in terms of neutral atom technology, also hosting 2 Nobel Prize winners here in Munich. And we have 2 flagship projects. One is with the German Aerospace Center. That's a contract which we won. This was a European-wide competition where we built a 100-qubit quantum computer, which should be finished till beginning of 27. And the second project, together with Dieter Kranzmüller at the Leibniz Supercomputing Center, that's our actual flagship project where we want to build a quantum computer with 1,000 qubits, so even a factor 10 more than what we did for the German Aerospace Center. And a very exciting project because it also includes the entire software layer, how to include a quantum computer as an accelerator next to CPUs, GPUs in a high-performance computing center. And last point, I also mentioned we have a big portfolio of quantum use cases. So if some of these use cases sound interesting to me, please approach me afterwards. We work on quantum machine learning, for example, in particular for climate simulations. We have 4 consortia in the logistic optimization with the German railway, with the harbor of Hamburg and many more. Computational fluid dynamics, for example, is also a problem which is extremely computationally extensive, and you need supercomputers to solve this Navier-Stokes equation. Then, of course, material simulations. Here we cooperate with companies like Airbus and many more. We have a project with the European Space Agency on doing image recognition using quantum-inspired networks, and also battery simulations. So in order to speed up the mobility revolution, not to charge my phone every 6 hours, we need better batteries. And designing this from a macroscopic world, this is something quantum computers can do hopefully better than classical computers. Yeah, with this I'm already at the end of my presentation. I think hand over to Professor Kranzmüller.
So it's the first quantum computer we put into the data center. We wanted to learn how to operate quantum computers outside the experimental lab. And it's particularly here because on the floor above it is the supercomputer who has the connection and does it, works with it together. So about 1.5 years ago, we submitted the first job to the supercomputer, which was then using the quantum computer. So all these things together are actually, and I mentioned the ecosystem, also part of the Munich Quantum Valley, where it's a huge state initiative where we're bringing different modalities together, where we're bringing all these different people together. Even the software ecosystem needs to be developed. And while we are doing prototype software system, there needs to be somebody that does sustainable software. So that fits in, and it is all this collaboration between people from different fields and how we get them together. So where do they excel? What do we see already? Now, one of the examples here is Sudoku. That's always my example I'm using, and this is actually an example from our training with students. Computer science students learn how to program Sudoku on quantum computers. Why? You have a very simple initial state, which is where some of the fields are still empty. And you have a final state where all the fields are filled. And it's exactly with the labyrinth example. Yeah? Basically, the quantum computer tries all the possibility at once and delivers the result. And in fact, we can build this code today in a way that we are just limiting the field, the size of the Sudoku field, by the number of qubits we have. So with a 1,000 qubit quantum computer, we can do really large Sudokus already. And that's why we see already today the improvement. Of course, there are also practical things like traveling salesmen. This is what we see in logistics, for instance, or material sciences, where real people working today on codes, on first implementations, in order to get there once we have to scale the stability. So we are developing the computer science part parallel to the physics part, making sure that once they are ready, both together, we will have what we want to do here. This is exactly what we see here, and you can download even an application. There is a code on how to do the traveling salesman on quantum hardware. This is kind of one of these applications. So we see real applications today while we are still developing quantum computers of sufficient size. And as I said, this is the role model in a sense. Quantum is not only a system itself. For us, it's a part of the bigger computing ecosystem. There is HPC, there is AI, there's big data, and quantum is kind of one of these extensions that we put in. This is where our research goes. I mentioned QX already, and in fact there are many different systems. We also have an IO-trap-based system. We have one of the European quantum computers, which actually, if we take computational performance, this is the most powerful system in Germany at that moment. Yeah? We're not able to show it because we're still waiting for politics to make the first pictures. Yeah? But it is there, I promise you, and we're already working on it, and we're really eagerly looking forward what Alex and his team will deliver. So in a sense, I hope I was able to show you not only the combination of computer science and physics is needed, but also how we build an ecosystem where we bring quantum to real world and make sure that we can really use it for the applications where we need it. Thank you very much.